Okay, so I'm just going to have a quick run through the meshing side of this conjugate heat transfer case. So I've just generated a mesh in SnappyHex Mesh, and then I split mesh regions based on cell zones, and that gave me two zones. So now the 0 directory has got fluid and solid in it. Now, if I want to have a look at the mesh as it stands, I can use foam to VTK, which produces a VTK file. And so I can have a quick look at, for example, so that shows the pipe that we've got at the moment, and that's a 3D mesh, the pipe flow. And we can do the same thing for the solid as well. So let's just have a quick look at what else is going on there. Conjugate heat transfer demo. So we've got in the constant directory, we've got polymesh, which is the block mesh, and we've got the files associated with the fluid and with the solid. So that's in the constant directory. Same in system, we've got the solver files for the fluid and the solid. So this has been set up previously, so I know that runs. And the same thing here for the boundary conditions. So basically, I set this up previously, but we've got this is created by the mesh, by the mesher, and then this is the boundary condition files. So for the fluid, for example, with the velocity, we've got an inlet, an outlet, and a fluid to solid boundary. So that's no slip for the velocity. So this is just for the pipe flow. And if you look at the temperature, we've got inlet, outlet, fluid to solid. And then this is where it's coupled. We can use coupled temperature. I've used this for the boundary condition here. So that says fluid to solid because it's in the fluid region. If you go to solid, we've got the opposite. We've got the box, just the box surface, and then solid to fluid. So this is the coupling between the solid and fluid, obviously. And then the box region here is where we apply the heat flux. So we're applying a heat flux to the box surface to heat it up, and then we're allowing the fluid zone to cool it down. So yeah, I mean, so you need to bear in mind you've got two separate zones for solid and fluid, and so you need to have two sets of boundary conditions for both of them, and the same goes for in the constant directory and in the system directory. Let's get rid of that, and we can get rid of that. So once that's set up, it's just a case of running it. And so wrong one. So I can then run chtMultiRegionFoam and pipe that. Oops. make sure you're in the correct directory when you run that. So that is going to take a while, well, a few minutes. I can't remember how big the mesh is. I mean, it's not very large, but it's going to take 5 minutes or so to run. And when it starts, the iterations are a bit slower. So you can see it's doing 13, 14 on one of these on the solid part, I think it is. So if you look on the left here, you can see the fluid and the solid solver bits. And as it gets more converged, or when it gets better converged, it will run a lot quicker, and that number will go down for the solid part. So it will speed up quite a bit. But I'll just pause this for a sec and then resume when it's finished running. So when that's finished running, this one's done 700 iterations. Should be able to look at this, the convergence, and yeah, for some reason, which I'm not sure why, but it seemed to converge very rapidly after 550, and then it certainly sped up a bit then. And so it seems like the solid part converged, and then that was taking a lot less time. So so anyway, that's that run. Oh, it's saved at 600 iterations. Oh well. So then we can have a look at the flow solution. So in order to do this, I'm not sure if there's a better way than this. There probably is. But I'm converting it to VTK files, and then I'm going to read those in to Paraview. So go to VTK, got one for the fluid, and one for the solid. So I'm reading in the solution at 600, hopefully. So I can, well, if I start, I can look at the temperature. So that is the temperature of the solid. So you can see it varies due to the heat flux and the cooling. We can see straight away that the shape of the cooling pipe on the inside is cooling it down. And I could do the same for the pipe region. So that's a lot cooler, and if I rescale that, we'll see that's between 300 and 308-ish. It would be more interesting to take a cut through. If I do a slice through, get rid of that, and do the same for the solid, clip it, Z direction, inside out, get rid of the plane. So now just looking at the clips, if I rescale that one, we can see in the solid region the cooling effect of the pipe, the liquid flowing through it. If we clip on the pipe as well and rescale that one, you can see the temperature change in the fluid. So you can see straight away that it's got a colder core, and then it heats up towards the outside, and overall the temperature in the pipe increases. And of course, for the pipe flow, we can also look at the velocity flowing through there. So even though it's a fairly basic example, it's really quick to run. I mean, it's taken 5 minutes to run it, and we've got a test case where we can vary the heat flux into the solid block, and we can vary the velocity going through the pipe in terms of like the mass flow rate. And we can also change the temperature of the cooling fluid as well. So change it from 300 to something cooler. And so you could look at um, the temperature difference between inlet and outlet for various mass flow rates through it and that sort of thing. So yeah, that's a quick overview of this test case. So I've just done two separate videos, which are basically one is meshing and one is about the flow solver, and then this one just shows basically the flow solver setup and just a quick demonstration of conjugate heat transfer test case and how to set it up and run it and then analyze the flow solution.